We have already done this slide. I just want to bring it back up because most of the material we're going to cover today relates back to this, the law of reflection, this idea that the incident angle has to be equal to the reflected angle. And remember that those angles are measured from a normal line to the surface that the light is reflecting off of. Also, everything in this chapter is going to continue talking about light rays. We're ignoring the fact that it's a wave. There's like a wave that's hidden in there, and we're just pretending that we can say that wave is traveling in a certain direction, and we'll just analyze what that direction of travel, what effects other materials have on the direction of travel of those light rays. So, this slide, done. Good job. You did one slide after break. Yay, that's nice. It's almost like that thing where it's like, I don't want to do any work. And then you tell yourself, just work for 5 minutes. And then next thing you know, it's like, things are good again. Like we just did the first slide. That's kind of that first 5 minutes. And now we get to do kind of new things because we already did this slide as well, at least half of it. We talked about sort of how these light rays follow the law of reflection, hit the mirror, and you can trace all of the rays from different parts of an object and start to get the idea of how you're going to see an image. What we didn't talk about was the right side of this, where we start to learn some terminology and some sign conventions that'll help us do the math of all this a little bit later on. So, first of all, notice part B says there's something known as object distance, which is represented by little d sub 0, or O for object, I guess, and image distance, little d sub I. Big surprise what those might mean. If you look right above that, the distance from the thing that's creating the light, or that the light's originally reflecting off of, is the object, and its distance from the mirror is just d sub O. And the image is the thing you see in the mirror, which you'll notice they've got kind of faded out because clearly there's nothing really there, unless maybe you live in a Harry Potter universe, which we don't, okay? So you see an image. It seems like there's something back there. So it has a distance from the mirror as well, which we call d sub I. Those have to be equal to each other if we have a mirror that's a plane, a flat mirror. Of course, all mirrors are not, and as soon as we step away from that and introduce some curvature to the mirror, things get confusing, complicated, and will be the bulk of what we talk about today, okay? So image distance equals object distance. Notice a few of the points that are down there. Because this is a plane mirror and because that relationship is true, you'll see that the image is upright, meaning it's not upside down. It looks exactly the same orientation as the object. However, it will appear to be reversed left to right. So it's not up and down reversed, but it is sideways reversed, okay? Also, let's see, number 2, we already covered that one because that's that point, essentially. And then finally, the size of the image should be exactly the same size as the object, okay? As long as it's a perfect plane, that relationship should be true as well. I don't really think there's anything surprising about any of that, right? Like just common sense and living in the world for however many years you have now, 19, 20, 21. How many is it? I'm just curious. How old are you people? 19? Well, you can raise your hand. Let's take some votes. I'm just curious. 19? 20? Ooh, 21? Greater than 21? Less than 19. Yeah, I thought so. Less than 15? Oh, that'd be weird. Greater than 40? Huh? What, you telling me to raise my hand? Is that what that was? Uh-huh. I see that. Just both of you, get out. Separate sides of the room, just get out. All right? So, nothing surprising there. What we want to talk about more is the spherical mirror. The spherical mirror. What happened? Are you okay? What was that? Just a little yell. You need more break, don't you? Yeah, a little bit? Okay. The spherical mirror is, well, not a full sphere, but you could imagine if I take a little slice out of a sphere that happens to be made of a reflecting surface, that will be the spherical mirror. So this is just part of a much bigger sphere. The center of curvature of that spherical mirror could be thought of as the distance from the mirror that is equal to the radius of the entire sphere that's not really there. Okay? This thing known as the principal axis is a line that passes through the center of curvature and also passes through the center of the mirror itself. Nothing terribly hard there, I don't think. Just terminology we're going to refer to several times. Also, I see a little problem here at the bottom. Anybody notice it? Oops. Yeah, principal. Yeah. There's always a few people out there that are like, well, hey, grammar or spelling mistake. Something's wrong. It's principal at the top. It's not like an axis that has like, I don't know, things that it believes or subscribes to. It's not a principal axis. No, just get rid of that. That's terrible. It should be this. Ignore me completely. You've missed jokes, haven't you? You saw things and watched things and were around people who were legitimately funny over break, weren't you? And now I'm not even remotely amusing anymore. That's great. Sad. So you'll notice we're looking at two different types of mirrors here. The way these are on the slide, I will admit, is a little confusing. So let me draw a line that's right here so we can focus on them one at a time. The one on the left is the concave mirror, which means that if I look at the incoming light rays, we are imagining that they're coming from the left and hitting the reflecting surface like this. It's almost like it's bent such that the light rays are going into a slight cave, if you want to think about it that way. Okay, there's an indentation that they're going into. The other option is the convex mirror, and once again, we're imagining that the light rays are coming from this side, so the mirror is bent away from the direction that the light rays are traveling. Concave goes into an indentation or a cave. Convex is the opposite way around. Notice that the center of curvature for the convex is on the other side of the mirror. It's behind the mirror. It's in a space where there shouldn't be any light rays hitting. Okay? Nothing is actually happening back in that space. Why did I draw a circle-ish thing that was that shape? I have no earthly idea. Maybe I'm thinking of Dementors now or something. I don't really know what's going on. All right? So you get the idea, concave, convex. We're going to analyze each of these in maybe what might seem to be a ridiculous amount of detail in the upcoming slides. So we're going to start with the reflection that we see in a convex spherical mirror. A convex spherical mirror. This one is, I guess, the easiest of all of them. Just as a little bit of preview so you can sort of feel the outline that's coming, notice if you go to the next slide, we switch to concave and look at its basic idea. But then over here, we're going to revisit them once again and kind of get into the analysis of what the light rays are doing. So at this point, I just want you to get a feel for what the overall picture is and sort of where the image is located. So notice, once again, over here on the left, and I'm going to have to do a lot of like not drawing and maybe just pointing. Let's say that we have incoming light rays that are hitting this convex surface. And notice all of the incoming rays are represented as parallel to each other. So we're imagining that these are coming from an object that's far enough away that the light rays aren't spreading out. Okay? So thinking back to like, I don't know, let's say this is a light source. And if light leaves a source in all directions, and I were sitting really close to that light source, you can imagine that around me the light rays are sort of spreading out. They're getting farther and farther apart. In other words, they're diverging from the source. However, if I get far enough away and look at two adjacent light rays, and I'm over here, I can't really tell that they're spreading out. They appear to me to be parallel, okay? So we're imagining a case where I'm far enough away from the light source that the incoming rays hitting the mirror are parallel to each other. Everyone okay with that clarification, first of all? Yeah, looking around. I'm going to look around one more time. Yeah, sleepy. No, not sleepy, just yawny. I don't know what that means. No questions. Okay, you're good. Notice what the light rays do. When they hit the surface, what's happening at each one of these points? What law is being obeyed? Looks a whole lot like the law of reflection, right? In fact, they labeled the two angles here at the top one. If I draw a normal line to that point where it hits the reflective surface, the angle in equals the angle out, and that happens for every one of these. Notice this one comes in right along a normal line and would reflect well, directly back, so there's no real need in drawing that one, okay? Angle in equals angle out, and both of them happen to be 0. So if I'm sitting back here somewhere, sort of looking into the mirror, I'm going to see those light rays reflecting back at me, and I'm going to imagine that they're all coming from a source along a straight line. So if I were to trace all of these rays back, the reflected rays, you can see that all of them converge at one point behind the mirror. That point is known as, surprise, surprise, the focal point. The focal point is the point behind the mirror in sort of this imaginary virtual space, if you want to think about it that way, from which the rays appear to originate. So I see them as if they're coming from that point. I see an image at that point, as we'll see in just a little bit, and it appears as if light rays are coming from that image. In addition, just a little point of clarification, you will sometimes see focal point, capital F. It's talking about this exact location, but sometimes you may see the focal length, little f, which is the distance that that point is from the reflecting surface. Focal point is the point, focal length is how far that point is from the reflecting surface. I should apologize at this point. Not because I did anything wrong, but because textbooks, sort of on the whole, with regard to this topic, sort of have all done something wrong. In fact, they all like to use different notation. So if you were to pick up 10, 15, 20 different textbooks, who would do that? I have no idea. Actually, I do know. Hermione. Yeah, today is clearly Harry Potter themed. What are we going to do? So if you pick up all these books and just looked at the optics chapter, specifically geometric optics, you would find that they use all of these terms, but they may decide to use different notation for all of it, and they may even use a different sign convention, meaning that we may say something positive means a certain thing, and they may decide that same thing positive means something else, and that is terribly awful and frustrating, and I'm sorry. So what are you going to do about that? Be careful. Okay, that's about all I can tell you to do. We're going to go with a certain set of conventions as we work through this slide, the slides such as capital F and little f, specifically meaning something different with respect to a convex spherical mirror. If you look in a textbook, they might decide to just flip which one's capital and which one's lowercase. You never know, okay? So look at the words maybe a little bit more and make sure that the symbols agree with what you think it's going to be if you're looking at, say, homework problems or looking at a different textbook or even looking at our own textbook, okay? So I'm sorry. I apologize for all physicists everywhere with regards to this, not for other things. I don't know what else they've done. I have no idea. Okay? So that's the convex spherical mirror. Let's switch over to the concave spherical mirror. Once again, light rays are considered to be coming from a distant source such that they're parallel to each other once they hit the mirror. So they're coming from somewhere on the left. And notice at every point of impact on the mirror, every reflection, they're once again obeying the law of reflection, every one of those individual light rays. So you see the angle in equals angle out, and if I trace all of those back, well, they all go to a point once again that's described as the focal point. That sits a certain distance away from the reflecting surface, that's called the focal length. So the only thing that's changed is sort of what the rays are doing and where they end up. The terminology is still exactly the same. There is a critical difference, however, between what's happening with the light rays on these two slides. Let me point out, in this case, all of the blue lines that you see there, none of them are dashed, right? That's trying to indicate that these are actual rays of light that are hitting the mirror, bouncing off, and coming into focus at that particular point. Something is happening right here with actual literal light rays. Meaning that if I were, say, to put maybe, I don't know, like a little piece of paper at this point, these light rays would bounce off the mirror from something that's way off to the left, would bounce off and come to focus at this point. I would see an actual image of that distant object on the piece of paper there. Okay? Real light rays would hit the piece of paper and form an image. That's different from what's happening here. Notice on the left, I have incoming light rays that are coming from somewhere, and then they just bounce off and spread out. And nothing really happens with the real light rays. What happens is all behind the mirror, the focus is not using real light rays. There's no actual light that ever hits any of this space, including the focal point on the other side. What do I see here? If I'm over in front of this mirror, what am I going to see? What if you look into the mirror? Nobody has any idea, and that's fine. I think you know what you would see. You'd see something like, well, different, but similar to what you see with a plane mirror. You see something in the mirror, an image. It's as if light is coming from that object in the mirror, that thing that's in there, even though there's not actually anything there. So I wouldn't see something that's exactly like the object that the original light is coming from, but I am going to be able to look in the mirror and see some sort of image that's being formed by the light rays coming from that object. We're going to see in a second that the fact that this is spherical means this isn't exactly like the object itself. Okay, it may be upside down, it may be larger, smaller, it might be flipped some other direction. We don't know. We're going to figure all that out in just a second. Okay? Are we still okay? Get the basic idea of what's going on? Yeah.
So with the concave mirror, then the image you see, then you don't see the image, you see the object?
Okay, let me see if I can restate a few things. So, objects, real physical things. There we go, okay? The only reason I can see the object right now is because light rays are coming from somewhere else, bouncing off it, and getting to my eye, which allows me to see the object. Now, we're taking the object that's physical, light rays are hitting it and bouncing and going somewhere else, far away, and eventually hitting a mirror. Okay, so we're good so far. So what happens here is if I look into the mirror and try to see the light rays that are coming back off it, I'm not going to see anything that's clear. It's just going to be some sort of weird, hazy, reflective surface. But I'm not actually going to see an image of the object itself, where image is something that's created by reflected rays. Okay? On the other hand, in this case, well, not that one, but this one, if I look into the mirror, I see something focused that's virtual, that's an image that's not sort of really there. Okay? So object, physical things. Images are creations that are formed by converging light rays that are coming to focus in some way. Okay? I don't know if that helped at all. Or maybe I just went sideways and didn't answer your question at all. But what do you see on which one? With concave. What you see with concave is nothing. The only way I can see anything is by putting a piece of paper or something here, or maybe my hand to let the light rays hit. And then they'll bounce once again to hit my eyes so I can see that. Okay? Yes. What's point C? That is the center of this big sphere that's being formed by that little piece of mirror. Being a spherical mirror, that's part of the surface of the sphere that sits at the center of that sphere. Anybody else before we get into the depths of this? Okay? One little point of clarification, just to make sure that you're sort of aware of what we're looking at. Something known as spherical aberration. Notice this statement here saying that there's a bit of a qualification on the previous slides and what's coming up. This only applies to rays which are near the principal axis. There it is once again. Look at this. Yeah. Principal axis of the mirror. Meaning, like if I had a massive mirror that's like huge, the front of the room, right? So that light rays hitting it, like many of them were far away from the principal axis, we wouldn't get a good focus. Only the rays that are relatively close to this axis are able to come together and hit a focal point. Notice they're describing here what happens if the mirror is too large, even though sadly they're using a drawing that's about the same size as on the previous slides. So here we're imagining that this is too large. Many points of mirror far from the axis. Still, the law of reflection is obeyed, but notice they don't all converge at the focal point in this case. If, on the other hand, I were to do something, I don't know, like maybe put like a screen here that sort of blocks some of the light rays so that the only ones that can actually hit the mirror are relatively close, then we do get focus at a focal point. Okay, it's almost like we have to make a little aperture for only those light rays near the center to hit if I want focus. So really what you get is that if you have a large spherical mirror, you're not going to have a sharp image that you see. It'll be blurry. It won't look terribly good. Okay, you might not even be able to tell what it's an image of, depending on how many of those light rays you have that aren't coming into focus and that are sort of obscuring what's there. So you'll notice there are two solutions to this. One I already told you is restrict the incoming rays to only those that are really close to the principal axis. Or you can change the shape of your entire mirror, which seems like a lot harder solution, and yes, would be harder to build, and make it parabolic shaped. In that case, it actually all does have one focal point, no matter how large that parabolic shape is. We are not going to be dealing with the physics of the parabolic mirror, so don't worry about that, all right? We can do all sorts of stuff with spherical mirrors as long as we sort of keep in the back of our mind, make sure you're not dealing with light rays that are too far from the principal axis, okay? Any questions? Everyone still good? Yes. Uh-huh. Not in the mirror. In this case, you'll see something perhaps, but it won't be in focus, okay? Oops, clarification. That is a concave mirror. So in this case, if I were to put, say, a screen here and try to see the light rays in focus, you'd see a blurry image at that point. You'd still see nothing if you look into the mirror itself, okay? All right, to the details. In the coming slides, we are going to start by looking at a qualitative method to try to figure out what sort of image you get that's created by different spherical mirrors. Later, several slides later, we're going to look at a quantitative way. That's where we'll finally have an equation that actually allows you to calculate these things. These two methodologies should work hand in hand. So we take a lot of slides to sort of qualitatively look at it because you need to understand what the light rays are doing. It helps you understand what sort of image formation you get. But whatever solutions we get from the qualitative method should agree at least somewhat closely with our exact calculations using an equation. If I just jump to the equation and let you calculate, you really have no idea what the light rays are doing and how it's making an image and anything that's really happening, okay? So think of these two things as working hand in hand. The qualitative method that we use is known as ray tracing. Ray tracing just meaning we're going to pick out some of the rays that are hitting the mirror and sort of see how they reflect and what they do in an effort to help us form the image that's created by the mirror. So notice it says we're using representative rays. Whatever object is far off in the distance creating all these light rays or maybe having light reflect off of it before it gets to the mirror, there's a bunch of them. There's an infinite amount of light rays if you want to think about it that way. We're just picking some. Specifically, we're going to look at 3, okay? The first one of these is known as the P ray or the parallel ray. It is a ray that is incoming parallel to the principal axis and reflects back through the focal point. Incoming parallel to the axis. So notice our P ray here. Well, that's pretty easy. It's parallel to the axis. Or if I look at a convex mirror, there's my P ray. It is parallel to the axis. The incoming part of the reflection situation has to be parallel to the axis. Any confusion happens after the reflection. Notice it says it has to reflect through a focal point. Well, that's pretty easy here because I can imagine, oh, fine, my focal point is there. It'll just reflect off and go straight through it. Not a problem at all. However, for the convex lens, well, once it bounces like this, there's no way it can go through a focal point on this side. The focal point is over on the other side. So I have to take the reflected ray and imagine a full line being created by that reflected ray, and it's in such a direction that that line will pass through the focal point on the other side of the lens. Okay? The key is separating the incoming lens, or the incoming ray from the reflected ray. The incoming ray is parallel. The reflected ray somehow needs to pass through the focal point. Good so far? You're going to get to do drawings when you're working through this part. You like to draw, right? You can probably draw better than I can. No, you can't? You promise? Worse? Huh, interesting. We should have a draw-off that would be just awful in every way. Be like the inverse of Pictionary. Like you don't want your people to guess the answer. That'd be kind of fun. Let's look at the second ray, the focal point, or F ray. It is incoming through the focal point and reflects parallel to the optical axis. So you can think of this as sort of the inverse of the P ray. It's doing the exact opposite thing. So notice, for the concave mirror, we show it coming in through the focal point and then reflecting back off parallel to the axis. That's pretty straightforward. It's the other one that's a little bit weird. Okay, I need the incoming ray to point at a focal point. Well, notice there's no focal point on this side, so what I have to do is aim it at the focal point on the other side such that the line that's created by that ray passes through the focal point, and then the reflection goes back parallel to the optical axis. So you can start to see that the convex mirror is the one that's a little more, what's happening here? The concave mirror, it's like it just perfectly obeys the rules, and there's not really a lot of confusion with that, okay? The last one, the C ray, the center of curvature ray, is almost just dumb, okay? Notice what it does. It passes through the center of curvature and then bounces back along the exact same path. So it's like, oh, look at this. It passed through C, keeps going to the mirror, and then just goes straight back. Yay, that's exciting, okay? Over here, because the center of curvature is on the opposite side of the mirror, again, we just point it at the center of curvature. It hits the mirror and goes straight back, okay? 3 different light rays that we're going to use to analyze how a mirror, convex and concave spherical mirrors, create images. Does anybody have any questions? No? Still good? Okay then. So, let's start with the convex. We'll start with the convex. Locating the image from ray tracing. Okay? So here's what we're going to do. Notice, here on the left, we have an object. And this is commonly the way that an object is drawn in a ray tracing diagram. Notice they just drew an arrow to sort of indicate, I guess, this side up, if you want to think about it that way. Maybe there's actually a person here. I don't know. Like we get to try some art. Isn't that beautiful? Yay, there's a person there. You get the idea. The arrow is just a simplified way to denote that there's an object somewhere that's physical sitting out in front of the mirror, okay? You're fine with that, right? Yeah, okay, maybe, why not? The length of the arrow is actually telling us something about the size, the physical height of the object itself, okay? So it's not completely nondescript. It's actually telling us some information. We're also saying that the upward side of whatever the object is this way instead of it being upside down, okay? Now, we're going to start at the top of the object and imagine that our 3 representative rays are leaving the top of the object and going and following the rules that we saw on the previous slide. Now, if that bothers you a little bit and you're thinking like, why just the top? Well, it's going to allow us to locate the top of the image. Just imagine that this is really happening from every point of the object, but I don't think anybody really wants to go through and analyze, what about light leaving this point, following the 3 things, and it's like now I find that point of the image. Just doing it for the top is enough to help me understand how the image will be created, okay? So let's start with the P ray. The P ray, it leaves the top of the object, goes parallel to the optical axis, and then reflects in such a way that the reflected line should go through the focal point. So you can see it obeys the rule pretty clearly there, but you sort of have to trace it back and use this idea that it's forming a line throughout all of space. If we look at the F ray has to have an incoming ray that points to the focal point. So you can see we have to trace it through to the other side. And then does the opposite thing of reflecting back parallel to the optical axis or the principal axis. And then the C ray, again, leaves the top of the object, just goes straight toward the lens in such a direction that it would go all the way through the center of curvature and then reflects back along the exact same path. Okay? Does anybody have any questions about how we followed those three rules for those three rays, first of all? There's a lot of lines up there. Yes? The C ray basically goes through the center of curvature of the mirror and reflects along the exact same path. So you can think of it as sort of hitting the mirror along a normal line such that it doesn't actually go back along a different path. Theta is 0. Yep. Good. Anybody else? Notice, I'm going to answer your question first. Yeah. The gray dotted line? Yeah. So this line here is showing the direction of the incoming F ray. Yeah, this green dotted line is sort of showing the line along which the reflected ray is traveling. So if you want to think about all of these light rays as just sort of being a line that's infinite in both directions, that'll maybe help you get to the answer. Do you see the magic that happened here? Okay? Images are created by the reflection. So we're looking at where the reflected rays come together. You can see that that's the first point at the bottom. The tip of the image, the top of the image, is at the intersection of the reflected rays. So look at the ones that have bounced off. So the P ray, you can see, traced back, goes to this point. The C ray, its reflection goes back to this point. And the reflection of the F ray is back to this point. Where do those three reflected lines converge? And you can see they all come to this one point right here, which represents the top of my image. Got it? Okay. Notice, everything on the right side of the lens, or not the lens, but the mirror, is dashed. It's dotted. It's faded out a little bit. There is no actual light on that side. So over here we have actual light rays. Back here, there is no light. Nothing could get back there. It all reflected off the mirror. This is the space inside the mirror where nothing actually exists. Okay? Notice that is where my image is. This image is not a physical thing. I can't there's the mirror. Let's go back behind oh, look at that. There's the reflection of me behind the mirror. There's nothing back there. That's a weird, odd space where something is happening, but there is no light that's back there. This is what we call a virtual image. In other words, it's not real. It's a virtual image that lives in virtual space being formed by no actual light. There is no light that's passing through the tip of that image that we've drawn. Your question? Kind of depends on what you're given. Right? So to be able to do any of these lines, we're going to need F and C. So hopefully they're already there. Without them, you can't really do anything. Anyone else? Yeah. It's a good question. Well, it's kind of the opposite of what we see here, right? Because if I look into this mirror, I'm going to see a reflection, but it's actually, the reflection of it seems to be closer than the object itself actually is to the mirror. So that's the opposite of that statement that you see. If I have a concave mirror, you're going to get an image that's maybe back farther, so that the actual thing is close, but the image you're seeing is farther away. Hopefully we'll actually see that pan out when we look at the other case. Okay? So virtual images indicate no light is passing through that image that you see in the mirror. One other way of thinking about this is the only way to see this is to look in the mirror itself. Only can be seen in the mirror. Okay? You'll notice that the next slide is about concave. There's only one slide here about convex, which means that this is what happens in all cases for convex mirrors. It doesn't matter if the object is close to the mirror or a medium distance from the mirror or very far away from the mirror. You will get something that looks like this. You will get an image that's virtual, meaning it's behind the mirror, it's inside the mirror. It'll be smaller. You can see the arrow of this image is smaller than the arrow of the actual object itself. And it'll be upright, meaning it's not flipping it upside down when you look at it in the mirror. This happens for all cases for convex mirrors. Weirdly enough, it's the concave that's actually more confusing. Depending on how far away the object is, it behaves differently. You get image formation that is different. So, you will see on this slide and on the next slide 3 different cases. First of all, if my object is farther away from the mirror than the center of curvature. So this is the farthest possible case. The second one is if I have an object that happens to be in between the center of curvature and the focal point for the concave mirror. And then on the next slide, in this case, I didn't write it here anywhere, but you'll notice my object is closer to the mirror than the focal point itself. Okay? So 3 different ranges. Greater than C, in between C and F, and less than C. We've got 3 different cases that happen. So let's take a look at what happens to the light rays. First of all, here's the object far away. The P ray hits the mirror and reflects back through the focal point. And the only other ray that they're showing here is the F ray, which the incoming has to go through the focal point and then reflects back parallel to the axis. Those 2 lines converge at one point. I could actually draw the C ray as well, which they didn't do, and it should be at least reasonably close. You can see it would go through the center of curvature. It's just that there's no mirror down there to reflect off of, which I guess is why they chose not to do that. And it would go back through and actually converge at the exact same point. Okay? Look at this image. This image is not behind the mirror. It's in front of the mirror. It's on the same side of the mirror as the object itself. Notice it's smaller than the object. That arrow is shorter. And it's also flipped upside down. Okay? How do we see this image? The only way we can see this image is by actually allowing these real light rays to converge at this point and then look at them. Okay? In other words, what I could do is put a physical screen here of some type. Maybe it's just my hand. Maybe it's a piece of paper. And this image would be formed at that point on the screen. This is what's known as a real image. A real image is formed by actual light rays. It's not virtual. It's not something that's hiding inside the mirror. It's actually light hits the mirror, reflects off to some point in physical space that if I put something there so that the light rays can focus on it, then I can sit back and be like, oh, look, there's an upside-down, smaller version of that object that's far away. Okay? So another example of this is if we were to take, say, a concave mirror and maybe just like hold it up to a window. Okay? We could imagine that the outside, if my mirror is like this big, the center of curvature might be like here. Like the entire outside world is farther away than the center of curvature. Okay? What we could do then is just hold the mirror up and then maybe hold a little piece of paper like in this location and then look at the piece of paper and you would see the outside world just reduced and upside down. It would be a real image formed by light rays on a piece of paper, and that image is in the real world, right? The piece of paper and the light, it's in the real world. It's not behind the mirror in some sort of virtual fake space. See the difference? Real versus virtual. I think it's the real image that often confuses people for some reason, because we always like look in a mirror. That happens all the time. We're accustomed to virtual images, even though they're the weird one. The real image is actually real light. It's just you don't often, stand very far from a mirror, right? How useful would that be, right? I'm over here. There's my spherical mirror, and then there's like a screen that's like right up there that has an upside-down version of myself being reflected, and then maybe I take a camera and point it at that and put that up on a screen, and I turn the screen upside down. It's a convoluted situation. So real images, at least in this case, maybe aren't terribly useful for looking at yourself, but in other cases, they might come in handy. So light is passing through the image, so we have a real image. The same thing is true if I go between C and F. Let's trace the rays once again. So starting with the object, which is between C and F, the P ray goes parallel, reflects back through the focal point. The F ray goes through the focal point and then reflects back parallel. The C ray here isn't terribly useful, right? If I go through the C ray, there's nothing over there for it to reflect off of. So we're just going to leave that one out, all right? Those two by themselves still converge at a point, which tells me where the image is. Notice this time, it's once again a real image because real light rays are passing through that point. It's upside down or inverted, and it's larger than the object itself. But I could put a piece of paper back at this location and see a bigger version, albeit upside down, of the object itself. Okay? Are we good with these two cases? Yeah. That's too broad of a statement for me to say yes. Trying to think of a case where it's not. Let's wait until we get to lenses and see if that plays out. Off the top of my head, I can't say for sure. Anyone else? Okay. Third case. Third one's the weird one. All we're doing here is like marching the object in closer. It started far away, then it's between C and F, and now it's closer than the focal length of the mirror itself. Notice what these rays are doing. They are a bit convoluted and strange. Starting with the parallel ray, the P ray starts parallel, and then has to reflect in such a way that it goes through the focal point, which is back behind it. Okay? Then you can take that light ray and say, ooh, if I trace it backwards, it goes back to this point. Okay? The C ray, well, it just goes bang, bang. Just bounces right off the mirror. The F ray, well, what are we going to do with the F ray? If it starts this direction, there's no focal length in this direction for it to go through. The only thing I can do is start it off in a direction such that if I trace it backwards, that line passes through the focal point. Okay? And then it reflects through the parallel to the axis, rather. If I just look at these reflected rays, I can immediately see that on the left side of the mirror, they're spreading out. They're never going to come to an intersection point on that side, which leads me back the other direction so that if I trace them back behind the mirror, we see there is a point where they intersect back there. Okay? This is behind the mirror. This is a virtual image. It's not real. Notice it is upright. It's in the same direction as the object, and it's also larger. How do I see this image? You look into the mirror. Okay? The only way you can see that is by looking into the mirror, and you'll see a bigger version of the object itself in there. Okay? So for these two slides, just imagine maybe a mirror on that side of the room, and you're taking an object that starts far away and then gets to this intermediate distance between C and F, and then gets even closer. For the first two cases, like in the mirror itself, it's just a hazy, blurry nothingness. It's only when it gets inside the focal length where you can look in the mirror and actually see something. Okay? I think that allows us to do this little summary, and that'll be a good stopping point for today. So, spherical mirrors, what do you get? Notice, for convex there at the top, there's only one case, meaning I can put the object anywhere, and these three things are true. It's always virtual, smaller, and upright. So the convex is the easy one to remember what's going to happen. It's the concave that you can go to these different ranges, and things start inverted when they're farther away and then flip to upright. The image goes from real, if I'm far away, to virtual when we're inside the focal length. And then you'll notice what happens here with the image size. If I'm far away, I get a reduced image, and then if I'm right at the center of curvature, it works out to be the exact same as the object, and then it gets even bigger as I go between F and C. But then I kind of like these 2 points. Notice the focal point itself causes some problems. So as I get closer and closer to the focal point from afar, the image gets bigger and bigger and bigger and bigger and bigger. And if I were exactly at the focal point, I wouldn't get an image. It's like it's gotten too large for it to focus on anything. There's sort of an asymptote that happens there. As I get to the other side of the focal point, well, what happens now is that image comes back into a size that's recognizable once again, and is smaller than it was before, but notice it's still larger than the object itself. So it's that focal point F that causes problems, and there's sort of a discontinuity in the image. Yeah?
Does approaching infinity mean that the light rays, the reflected ones, is never converged?
They're converging, but it's the image size that's approaching infinity. So if you're imagining it's an image of a person being reflected, they're getting taller and taller and taller, and now it's like, well, the image itself is too tall to measure.
So how is that working trying to affect
How would the reflected lines? Let's go back to, this one. Let's see. So if we looked at this, if I move this closer and closer, you could probably just do a couple of these and imagine like if I put my object right here, you should see an image that's farther back, and this line would be getting taller, but still upside down. Okay? And then if it's exactly at F, it's like, well, I can't draw a space large enough for them to ever converge back there. Okay? We're done, unless anybody has questions. No? All right. Goodbye. You made it through a lecture on the other side of spring break. Congratulations. So let's flip over to the next slide, and let me tell you how to solve this analytically. We need a pencil. How to solve this analytically. So it's the same stuff. We're dealing with mirrors, specifically spherical mirrors, where we have just like a slice of a sphere. And what I didn't give you was any equation. So there are two equations that you're going to need to know to be able to solve these problems. So first of all, surprise, surprise, the mirror equation. And it is quite straightforward. 1 over dO, the object distance, how far the object is, the physical thing from the mirror, plus 1 over dI, the image distance, how far the image is located from the reflecting surface of the mirror, is equal to 1 over, and think of this as like a curly F. It's distinct from the other two Fs that we've already had back several slides ago. Okay? So we had the focal position. Remember, that's the place where the parallel light rays can come together. That's a location somewhere in vicinity to the mirror. We had the focal distance, which is how far that point is from the mirror, and I used lowercase f for that. This is related to focal distance, but it adds a little bit of information. So this is still how far away the focal position is from the mirror, but plus or minus on this tells you some additional information, as you see down below. Okay? So let me make a list of these. We've got capital F is focal position. And I'm sorry, once again, this does get confusing. Then regular lowercase f is focal length. And now we have curly lowercase f, and I'm certainly going to mix those two up when I'm writing equations and doing algebra, so forgive me in advance. I messed up this already, didn't I? Look at that. This is focal distance. I know, it's confusing. And this one is focal length. Okay? Focal position, that's the spot where the rays come together and converge. Focal distance is how far that spot is from the mirror. And focal length is the same as this with a plus or minus to give additional information. And you can see that if it is positive, you know you have a concave mirror, and if it's negative, it's a convex mirror. So you'll have to put in the positive or negative if you know what type of mirror you're using, or maybe if you know the other things, you know where your object and image are located, whether this solves for a plus or minus tells you what kind of mirror is involved. Okay? So there's additional information hiding in the sign. Got that? Okay? One additional equation to put on this slide, and that is for magnification. Magnification M is equal to negative DI, the image distance, over DO. And it's also just equal to the height of the image over the height of the object. So we'll call this the height or size of image, and this is of the object. So magnification, it makes sense, just like how big the image is compared to how big the object is. Is it bigger? Is the image bigger? It's magnified. Is the image smaller? Well, then I guess you could still say it's magnified, but magnified in a degrading way. The image is smaller than the actual object itself. All right? A couple of other things that this tells us. First of all, M is just a factor. Or let's call it a multiplier. Why not? In other words, if magnification is 1, image and object are exactly the same. If it's 0.5, the image is half as big. If it's 2, it's twice as big. Okay, so it's just a multiplier on the size of the image compared to the object. One other thing is that if you get a plus for the magnification, then we can say the image is upright. And if it's negative, the image is inverted. So that's all the stuff for magnification. Okay? And if you're thinking like, this is a lot of stuff to remember, it is, but you're going to get to use it twice. In a way, a lot of this works for mirrors, but also for lenses, which we're going to cover today. So there's going to be a lot of sort of repeat information as we go through today's lecture. And then here at the bottom, you also get information from the sign of the image distance and the sign of the object distance. Okay? Notice, for the image, if you end up with a positive image distance, you know that is a real image. In other words, it's an image where the physical light rays are hitting something like a piece of paper and putting an image on that piece of paper. If it's negative, you know you have a virtual image, which means the only way you can see it is to look into the mirror and you see that image like in mirror space, if you want to think of it that way. It's nothing that's really there. Which leaves us with these bottom two, and you might see something there all the way at the end that sounds a little odd. Yeah? Something bother you there? Yeah, I agree with that. We're going to focus on this one because this is typical, right? Something physical is in front of the mirror. We have an object that's an actual thing sitting a certain positive distance in front of the mirror. A virtual object is a little bit weird, and it's going to come into play when we have things like microscopes and telescopes, and we're going to briefly talk about how those work probably on Friday. When we have, how to describe this? When other mirrors or lenses create an image, and that image is being used as the object of another lens or mirror, we call that a virtual object. It's not something that's really there, and it works only in compound systems. That'll make more sense a little bit later, so let's just hold off on that later, okay? So right now we're only going to have virtual objects, so you'll always have a positive object distance. Who's got questions about anything on this slide? Because I've probably twisted my words a few times and said the wrong phrase and didn't mean something I said. I'm waiting. There it is. Yes.
When you said negative is when image is inverted from magnification, does that mean horizontal or vertical?
That's always going to be dealing with vertical here. Okay, so for mirrors, it's always going to be inverted sideways. But it could be upright or inverted vertically. Yes, I think we're on the same page. Anybody else? No? Oh, no? Nobody? Oh, thought there was a question. Maybe not. That is the end of mirrors. Okay? So the same exact sort of list of things or procedures we're going to go through is going to apply to lenses. It also parallels what we did in the last chapter. The first half of the last chapter was reflection. Well, that's what we just dealt with mirrors. The second part of the last chapter was refraction or bending of light rays. Well, that's what we have with lenses. So it's almost like in this chapter we're doing the same stuff, but we're dealing with the physical objects that use these two effects to some advantage. Okay? So, lenses. First of all, the couple types of lenses we're going to use. We should start by describing what a lens is. It's just going to be a relatively thin, transparent substance, probably a clear plastic or glass in most cases, that is using the law of refraction, or Snell's law, to redirect light. We're using that bending of light to try to get it to focus, perhaps, at a certain point. And two types of lenses we're going to look at. First of all, the converging lens. Converging lens does exactly what you would expect by trying to bring light rays together. It tries to make them converge. So you can see there, if I have parallel rays of light that hit a converging lens, it will bring them to a focus at a point. So in other words, we might have a situation that looks kind of like this. Let's say we have an axis, and on that I put a lens, and we'll just kind of use this to represent a converging lens. As you can see, that kind of looks like what's over there. Why not? If we had parallel light rays that enter that lens, again, that's going to happen if the object is far away. They're essentially parallel. You could imagine there is some point over here where it will cause those rays to converge. And I'm going to stop drawing the rays at that point. Obviously, they'll hit that point and start spreading back out again. So if you wanted to think of the fact that, yes, they're going to keep going that way, that's fine. We're not really worried about what they do next. They do focus at a particular point, and we're going to give that point the letter capital F once again. That's the focal position for that lens. So what happens if we do something like this? Let's again draw an axis, a bit of a wavy axis, and a converging lens. And let's say my focal position is here. And perhaps I have a source of light at the focal position. So imagine there's maybe just a light bulb that's sitting at that spot a certain distance from the lens. So if I have a light bulb, you can imagine light is sort of spreading out in all directions, which leads us to something we haven't really stated, even though we've implied it many times. If I have light that's coming from a source, it diverges from a source. Whether that be a single light bulb or whether that be the iPad sitting here, light starts at a point and spreads out. The light rays get farther and farther apart the farther away you get from the source. So we could draw a few of the light rays that are spreading out from the source, and let's just look at the ones that are heading toward the lens, keeping in mind there are some going all the other directions as well. The lens is going to converge the light rays. So instead of them spreading out, it's going to have the effect of bringing them together in some way. Well, what happens is exactly the opposite of what you saw on the other side. They will leave the lens traveling parallel. In both cases, we're going from a case where they're in one configuration and they're going toward moving closer together. Okay? Thoughts, questions? Comments, complaints, any words at all? Are you glad it's Wednesday? Do you wish it was Friday? Do you wish it was next Wednesday? Do you wish it was next Friday? Yeah, that sounds a little better. I understand. Got to finish up that exam. It has to happen soon. There is a draft out there, but it's not quite complete yet. So you still have a chance to bring donuts and coffee. Nah, sorry, we can't do that. So notice on the right, these are just some specific converging lenses showing that it's possible to have a situation where both of the sides of the lens, there's a front and a back of the lens, are bent the same direction as you see here. So it's still, it's basically convex on both sides. It's possible to have a convex shape on one side and then flat on the other. Or we can have convex one direction and then convex the other direction, or concave if you want to think about it from the left. All of those shapes will act as a converging lens. So if you get in the lab and you're handed a big pile of lenses, who in the world knows? And they're like, get a converging lens, you've got some options. Okay? They might not all have this common shape where that sort of goes out on both sides. All right? The opposite of this is the diverging lens, which does exactly the opposite. It's going to spread light rays out. So we could say that it takes parallel rays of light and spreads them, what happened to them, out as if they are coming from a particular point. And, of course, that point will be the focal position. So So let's draw a diagram once again, or a couple of diagrams. Let's see. So a diverging lens, kind of the common shape is like this, where it's concave on both sides. And we're going to start with parallel rays of light, as if from a distant source. And then they're going to spread out as if they had been diverging from the focal position. So in other words, it's going to look sort of something like this. Oh, yeah, this whole diagram is kind of falling apart, but hopefully you'll get the idea. Those two on the edge kind of barely went through the lens at all, almost missed, but hopefully it's enough to give you the idea. If I take the diverging rays after they pass through the lens and just trace them all backwards, it's as if they're coming from the focal point. So let's put an F there to represent that. So what do you think happens if we flip this thing around? So let's draw this once again. I'm getting tired of drawing things today. I don't know about you. It's too much drawing for a Wednesday. I like to keep my drawing to Mondays and Fridays. I don't know, that makes no sense and has no bearing on anything, so just forget I said it. So let's say we have rays of light that start by converging. So let's imagine that they are heading toward the focal position on the other side. So in other words, we've got a ray of light here that's going that way, and maybe one here that's also heading at that point, and maybe one here. And hopefully I can stop talking and you get the idea of what I'm drawing. Oh, that one was terrible. Stop it all. I deleted too many. That's all right. Okay? So they're converging toward the focal point on the other side. Well, the diverging lens isn't going to allow that to happen. It's going to spread the light rays back out, and you might be able to guess that instead of them continuing toward that point, they will emerge on the other side parallel to each other. Okay, so if they start parallel, they'll spread out on the other side. If they start more together, more converging, they will spread out such that they're parallel. Okay, the diverging lens. And you see a few examples there on the other side. Again, both sides can be concave toward the left, or one side could be, or you can have concave both directions. All of those will act like a diverging lens, right? So I feel like we should play a game, bucket of lenses, and that sounds like a sad, terrible game. We're not playing that. We should play games in here, though, shouldn't we? Like two people are nodding and the rest of you are like, no, I'm here to learn physics. I'm not going to do any of that. Games. It's ridiculous. Who wants to play games? It's terrible. You do want to play games? Anybody have any ideas? Something we can play that's educational? You're like, no, not educational. Physics Jeopardy? Sounds like work. I'd have to build that game out and come up with questions, and I guess I could source questions from all of you. Then you'll know some of the answers. But I'm done talking about this. Maybe we'll play a game one day. Ooh, what was that? You had an idea? I'm scared. What is it? Huh? I don't need to know? Okay. I'm just going to go over here now. I think it's safer over here. Question? I can. There we go. Converging light going into the converging lens. Boy, that is an excellent question. It depends on the exact lens, but it's going to converge it even more. You might just end up with a mess. I can imagine a case where the light it's going to like bend it out even farther. Maybe it even has total internal reflection in some cases. So, same thing for the diverging lens. What if it's diverging already? Same idea. More spreading, and it could be so extreme that the lens kind of kills the beam altogether. Yeah. It sure looks like it, yes. So you could have one lens that works both ways, depending on which side you shoot the light into. Anybody else? Good questions. That's nice. You wanted to get back on topic, didn't you? Yeah, I see how this class works. Just serious people. Let's talk about ray tracing for some of these lenses. So we're going to do the same thing and go through all the qualitative discussion and look at how the rays work. And then in the end, I'm going to give you the equations that you're going to use, and they're going to look terribly familiar. And then we're going to do an example, and who in the world knows if we're going to have time for all that today. We'll see where we end up, okay? So notice, we're going to start with convex lenses. Convex lenses or diverging lenses. Excuse me, converging lenses. Too many words in my head. Right? Similar rays as before. You have a P ray, an F ray, and an M ray. The P ray is going to start parallel to the axis, and then on the other side, it's going to pass through the focal point. That seems pretty straightforward. The middle one there, in the diagram at least, is the last one in the list, the M ray. This time starts at the tip of your image, goes through the middle of the lens, and just continues going. And then the F ray is going to go through the focal point on the first side of the lens, and then emerge parallel to the axis on the other side. Any thoughts about any of that doesn't seem to make sense? After looking at mirrors, that seems ridiculously straightforward, right? Or am I assuming too much? I see a few people still staring at it. Can I go over to the other one? Okay. How do these rays look for a concave or diverging lens? They're a little more confusing this time, but it's the same idea. So the P ray is going parallel to the axis in the middle. But since this is diverging, can't bend it inward toward this focal point. It has to spread it outward. So it's going to spread it outward such that that line will pass through one of the focal points. It's just going to have to be the one that the light originated on. That's the only option because it's spreading light out. The midpoint, or M ray, big surprise, goes right through the middle. Yay, exciting. And then the F ray, well, here we've got a little bit of a problem. Keep in mind, it's going to go, well, how to say this? It's going to go through the focal point on the opposite side every single time with this type of lens. The problem is it's never going to get there. It's just going to be heading in that direction, but it's going to emerge parallel to the optical axis or principal axis, okay? I've tried to make these descriptions here at the top a little bit longer, more lengthy to try to describe which focal point they're going to pass through and describe some of that extrapolation of the lines to help make things a little more clear, I think. So you've got more than just my verbal words. Hopefully the explanations up there will help as well. And we're going to look at several cases of all of this, right? So we've got diverging and converging lenses. Let's stick with the diverging lens a little bit and take a look at the possible options. You will notice there is only this one, much like what we had with, which mirror was it yesterday? I've lost track now. Was it the concave or convex? Where there was only one case for all of them. I know it's too many words just floating around inside, right? Was it convex? It was? You sure? So the opposite situation with lenses. So that's not confusing at all. So let's see here. This is diverging. And notice no matter where I put the object, we're going to end up with the case that you see above. Just like we drew on the last slide, you can see that we have this top ray, the P ray, spreads out but traces back to the first focal point. The F ray is heading toward the other focal point but goes parallel, and the M ray goes straight through. This diagram shows where the outgoing rays converge. That's the key. So if I trace this one back, it goes to that point. If I trace this one back, it goes to that point. And if I trace this part back, it goes to that point. The key is, where do the rays that have already passed through the lens converge, wherever that point happens to be. It has nothing to do with the incoming rays. They shouldn't converge at all, okay? So you can see the image there. Well, the image is smaller, So you can see the image size here below is reduced. It's pointing up just like the object, so it's upright instead of inverted. And you'll notice here on the bottom right, this is a virtual image. Virtual image, again, meaning that there's no actual light that's passing through that point. These light rays are all on the opposite side now. They're not physically converging here. I can't put a piece of paper there and get an image. So if it's virtual, if it's imaginary, if it's not really there, how do I see it? You all in the front are doing a great job of all staring at me. Except you. What's the deal there? Like all 6 of you, all of you are like, and you're down here. Like you're writing everything. So let all of you to get together. Ready? That's good. Now you're all staring, but you're not going to answer my question, are you? How do you see this image? Through the lens. Through the lens, which way? From the right or the left? From the right. Yeah, so if you put your eyeball over here, what's an eyeball look like? Oh, that's just a little bit horrifying. Let's make it just kind of extend off the screen. Now, I just don't know. Maybe, what else can we do to this? I guess I could just draw an eyeball like this. But then that's like extra creepy too, and it's not even looking to the left. Just draw a triangle? I don't know what's... I know. What do you want a triangle for? I'm so confused. What? You want it to be this way?
Yeah, and then draw the curve.
No, not there?
Inside.
All right. That's just Pac-Man. That's all we have there. Here? How is that an eye? That's not an eye. What is this, like eyelashes or something? Is that what? I don't know. The whole thing is disturbing. Anyway, look from the right, through the lens, and you see the image inside there. It's virtual. It's not really there. So if you think about this just a little bit, what's happening? It's like there's an object over there, a lens in the way, and I'm looking through toward the object. I don't actually see the object anymore, right? Instead, I see like another version of it that seems to be a little closer and smaller, but not the object itself. I'm seeing light rays that have been refracted and bent to form a new image. You should find this a little disturbing if you wear lenses of any type. I wear contact lenses. A lot of you wear glasses. I can at least see that. If you wear contacts, I have no idea. There's not like a light on your head or something. Who in the world knows? Do you ever really see the world then? It's kind of creepy, right? All you ever see is virtual images everywhere. So you're like, I'll take the virtual images that are in focus over the blurry virtual or virtual or real blurry images, objects. I'm out of words. I have no idea. You get the idea. So it matters not where the object is located. If it's close to the lens or far away, it's going to be in this configuration. Okay? Virtual, reduced in size, and upright. Okay? Let's switch lenses. If we switch lenses to our converging lens, there are 2 different cases depending on where I am compared to the focal position. So you'll notice this divides sort of in half here at the bottom. And let's start with the object location beyond the focal position. So you see that on the top left. So it's out somewhere past the focal position of the lens. Notice what the rays do. P ray goes this way and then through that focal point. M ray straight through, and F ray starts through the focal point, and then they all converge over on the other side. Notice we've got an upside down or inverted image. We've got a couple of options for image size. It could be enlarged or reduced, just depending on how far away we are from this particular lens. Okay? So you've got multiple options there. And in all cases here, we have a real image. Real image meaning If I am at this location with a piece of paper, it's going to actually draw, or the light rays are going to make an image on that piece of paper. I can't put my eye at that location and see anything. Nothing. That seem a little weird? Yeah? So if I look through the lens, you'd just be like, ooh, blurry everything, like nothing is there. But then if I put a piece of paper there, I can step back, look at it, and actually see something. This is kind of like, the projector. Right, the projector has a lens on the front. It's converging a bunch of light rays to give you an image that's in focus on the screen. Okay? But what if I were to take my eyes and put them at the exact position of the screen up there? And how creepy would it be if I just went, whoa, to put my... See, I should have set this thing up, because now we're on Harry Potter movie 2, right? So I should have been prepared to do a little magic. I can't get my eyes up there. But if I put my eyes there, am I going to see a nice, beautiful image? No, I won't see anything except a big, bright light. The light rays are already converged to this point, and my eyes have no idea what to do with them. We'll talk about that a little bit more when we talk about the human eye later in this chapter, okay? Let's see. So let's draw an arrow up to that one. And then these bottom two cases go with the diagram on the right. Now we're taking the object and moving it closer to the lens than the focal position. Closer to the lens than the focal position. Take a look at what the rays do. And they've only drawn two of them in this case. So you can see the P ray starts parallel, goes through the focal point. The M ray goes straight through, and they converge way back here behind the object. So that's going to be a virtual image in both cases, and it's going to be upright and enlarged in all cases, right? Since it's virtual, I again have to put my eye, how does this work again? Like this, and then we have to draw this here, and then maybe like an eyebrow. That's starting to be pretty good. I feel like an artist all of a sudden. Now I need to draw the rest of the face. Where do I put that? Now I'm confused. So I guess if that's an, I can't. See, I just wanted to just go, whoo, like that, but that kind of, guess that could kind of work if maybe I draw like a nostril here or something, and maybe I've got Voldemort all of a sudden now. That's no good. Sorry, I shouldn't have said his name. I'll take all that back. All right. Notice there's a situation where the focal point is a problem. Okay? As I approach the focal point from farther away, notice my image size is approaching infinity. It's getting really big. If I approach the focal point from the other side, it approaches infinity. If I put my object itself at that location, I don't get an image anywhere. All is lost. We kind of already talked about that, right? Take a look back here. Ooh, here we had my object sitting at the focal position. The light rays are spreading out. They hit the lens and then just go parallel. They're never going to focus anywhere. They're just going to go parallel forever. Okay, so you don't get an image at all if your object is sitting at the focal point. Okay? And that's all the cases for lenses. There was more with mirrors. That's all the cases you have. 3 different options in total for the 2 types of lenses. Any questions, thoughts, complaints? Now you're not all on the same page. It's a variety of stares and notes and people ignoring me and all of those options. Nothing? Okay. Quantitative it is. And we're going to do basically the exact same sort of thing. So first of all, this one's going to be called the thin lens equation. And the thin lens equation is basically the exact same thing as the mirror equation. So why do we call this one the thin lens equation? I don't know. Why not? We're talking about lenses at this point. It looks exactly the same. 1 over DO plus 1 over DI equals 1 over F. Oops, that should be kind of a curly F to keep things straight. Once again, the focal length is the same distance as the focal position or the focal distance is from the lens, but the plus or minus on the focal length is going to carry additional information telling you what type of lens you have. Diverging is the negative one. Let's see, magnification, we're going to essentially use the exact same equations as before, so let's put that down here. So magnification is negative DI over DO, or HI over HO. And you'll see that magnification is positive if upright, negative if it's inverted. And the same thing apply down below for the image distance. It's going to be virtual if it's negative, and we have a virtual object if the object distance is negative. So all of these same rules apply, and even the same equations, which is kind of nice. Okay, so you can carry over all that detail from the previous slide if you want to help solve these problems. Good? Should we do a problem now that I've talked about this for forever? Yes, maybe. Here's your problem. I'll give you a chance to read it, see what you think, and then we'll talk our way through all those parts at the bottom. Mm-hmm. You have a question? Yes. The negative on the DI? For DI and DO, it's virtual image or virtual object. For magnification? For magnification, if it's negative, you get a virtual image. But you'll plug in a positive or negative for DI and DO, and then if all of that gives you a negative, it's flipped upside down. That's a good question. Hold on. Let me fix something there. I'm using too big of an eraser. Let's back that up. That's just terrible, right? Let's see. Where's eraser size? How about this one? That's what it's actually supposed to be. That's my mistake. The magnitude of the magnification. So HI over HO isn't actually going to tell you any information. You have to use the other one to get the inversion information. Thank you for pointing that out. Good call. Same for mirrors, or for mirrors. So let's go back and fix that. My fault. Let's go here and do this. Get rid of that. There we go. Okay? So negative DI over DO for the magnification is what tells you inversion information, and you get nothing from HI over HO. So notice the part of this problem that I've underlined. What does this tell us about the type of lens? Or what does it tell you about the type of image you cannot see with this lens? Good job. I'm proud of all of you. It's well done. The way you just so quickly responded and said, the answer is blah. It's good. Is it a converging lens? Why would you say it's a converging lens? I would say it is, but why?
Because you can't see the image clearly at all, and that would probably assume that the size of the image is approaching clearly with only 5 converging lenses.
That's one option for a converging lens. Like if it was at the focal position, you wouldn't see anything, but right above here we've got our object is 12.5 centimeters, and the focal distance is 8.5. So we know it's sitting beyond the focal position. You can't see it. So what type of image can't you see? Understood, yeah. If you're looking into the lens and you were to see an image, what type of image is that? That's virtual. So there's no virtual image here at all. And it doesn't matter how far away I am or how close I am. If this object is sitting that distance from this lens, we could say that no virtual image possible. So if you go back and look at the options we have, here it's possible for me to have a virtual image, but you'll notice it has to be inside the focal position. That's the only option there, which takes me back here where I can be at any position, and I get virtual in all cases. So based on that, maybe I was thinking wrong. I said it was converging, but let me look at the answers here all of a sudden. 12.5. Okay, good. So if it can't be a virtual image, our option is either it could be here, that's one possibility, okay? Or it can't be here because I can't see a virtual image, okay? So our only option is a converging lens where we have the object sitting beyond the focal point. So let's write that down. Let's see, we have a real image when object is beyond F, the focal position or the focal point, which means this must be a converging lens just by sort of deducing what's happening based on our options. So that answers part one. Yay. That was exciting. Okay? Yeah. Virtual images are what you see looking into a lens or through a lens. And this says that no matter where I look into this lens, I never see an image. So there is no virtual image being created in any way by this lens. Yeah. One's just closer. It's just trying to say as you get closer to F, the image size is getting really, really big. So if I'm really close to F, just beyond F, it's going to be very large and real. Hugely tall. So you might imagine if we had a regular light bulb and we had this lens and we put the light bulb relatively close to the focal position and it was putting a real image over on the wall, it might be bigger than the room. Okay, and as I get closer and closer, you would see the image of the light bulb get larger and larger until it's too large for you to actually do anything with it. Okay. Can we find any of these things in number 2? Find F, DI, and M. Let's see. So what do we know? We know that the object position is 12.5 centimeters. And now we know the focal length is positive 8.5 centimeters because it's a converging lens. So once we know what type of lens it is, we can put the appropriate sign on the focal position or the focal distance to give us the focal length. And if I have those two things, we can use the thin lens equation to find the position of the image. So let's see, 1 over F equals 1 over DO plus 1 over DI. Plug those numbers in and tell me what you get for DI, since I'm out of space down here and don't want to do it myself. Someone get a calculator. Let's see if we're all on the same page. Since we have a real image, you should get a positive value. If you get something negative, then something's out of sorts in the problem. We're doing something incorrect. Good job, all three of you, using your calculator. Thank you. Someone's like, no, I'm number 4. There's 4 of us. This is good. The whole side over there, like none of you. You're like, we're not calculating anything. How's that side over there doing? Oh, there's a couple of calculators. Somebody tell me the answer. Hurry. 26.56. I like that. Let's say 26.6 centimeters. That's our image distance. It's positive. It's a real image. That's how far away it should be from the lens. Okay? That seems okay. So we've got F and DI. We can now find the magnification because we have DO and DI. So let's hop over to this other slide where I have more room. And let's see. The magnification is negative DI over DO. So that's negative 26.6 over 12.5. And that is going to give me 2.13. Comes out positive. So it's more than twice as big as the object itself. So we could say that it's enlarged and upright image. Okay? Yeah. It's a good question. How did it? That seems odd, doesn't it? Oh, there's a negative sign there. My fault. It's like right there next to the 2.13, and I didn't even see it. So it still is enlarged, but it is inverted. My bad. You're like, how did your math be so broken? Okay? So it's flipped upside down because of the negative, but it's larger by more than a factor of 2. So what else is in the list here? Let's see. Image size, we found... Did we find image size? Not quite yet, did we? Image size, we can just use our multiplying factor to find the image size. You'll notice that the light bulb has a radius of 0.51. So we could do something like this. We could say that the radius of the image is going to be equal to the magnification magnitude times the radius of the object. So that's going to be 2.13 times 0.51, which is 1.09 centimeters. Let's see. We know that it is a real image. We already did that. We know that it's inverted. We did that. Number 6 is draw a ray diagram. That sounds like fun. And see if all this makes sense. So here's the problem with just drawing a ray diagram by hand. We just did the whole thing analytically. We have exact answers. When I just sketch out some lengths by hand, they're not going to be terribly exact. So the idea is I'll be a little bit careful, but it's not going to come out perfect. So just be okay with that, all right? If we actually use something to measure the distances and got everything exact, it should come out really nicely. But we don't have that option. So let's draw our axis, and we have a lens in the middle, which is converging. And let's see, based on some of these distances we've got one that's less than 10, one's a little more than 10, and then something that's 26. So let's say that this is 10 centimeters, 20 and 30. See, we're already running into problems, right? We'll call that 10 this way, and that's 20, and that's 30. So this is going to be awful. Prepare yourself. We need to start by drawing the object at its location, which is 12.5 centimeters. So that would be, I don't know, roughly about here. There's my object. And then I'm going to draw the focal point on both sides, which is at 8.5 centimeters. So one of them is about here, and one is about there, we'll say. And then we're going to draw these rays of light. We're going to get a terrible answer. It's not going to agree with what we just solved for. And then we're going to be done for the day. And I'm going to see you all on Friday. So let's see. The P ray, for starters, starts parallel to the axis and then has to go through the focal point on the other side. So there's P. The F ray goes through this focal point. And once it gets to the lens, I ran out of lens. It goes parallel to the axis. Oh, it's roughly in the right place. And then the M ray has to go straight through. Oh, and then we're just going to kind of curve it a little at the end. How you like that? Yeah, that's fine. And it goes through there. And then we're going to say they all intersect about right here. Right? Which you can see is clearly exactly at 26.6 centimeters, exactly where it's supposed to be. Okay? Things that you can see that seem to be true is that it's inverted, as expected. And it also looks like maybe my upside down arrow is bigger than the object's arrow because it's supposed to be bigger, but it's supposed to be twice as big. That didn't really happen either, okay? Again, get a meter stick, draw straight lines, it comes out exact. Just get the concept, and it's okay, okay? Questions, thoughts? You have none. Get out of here. I will see you all on Friday. Goodbye.